So now moving into calculations, start off with writing the expression for the equilibrium constant in terms of concentration. So of course one just takes the righties over the lefties, multiply them together. Don't forget to put in that it is at equilibrium. And because we've got 2HI, we square that. So as units go here, you've got concentration squared on top, concentration squared on the bottom. They cancel out nicely. As illustrated in part B, where they tell us the value of Kc, just 46, no units there. Calculate equilibrium concentration hydrogen temperature given the equilibrium iodine and equilibrium HI. So we know Kc, we know HI, we know iodine, we can pop in to get hydrogen. Pop them in, rearrange, punch in our calculators. Hydrogen at 4.08 moles per cubic decimeter. So next one, nitrogen can react with hydrogen to form ammonia. We talked about this already from a different perspective. Mixture of N2 and H2 left to react at a certain temperature till it reaches equilibrium. The equilibrium mixture has this following composition. So part 1, a student said equilibrium must lie to the left because the concentrations of nitrogen and hydrogen are greater than that of ammonia. Is he correct? Now you can't do what the student did because you've got cubeds on the bottom and squareds on the top. You cannot just look at values and say what K is. The only way that you can do it is to actually calculate what K is. So let's justify our answer by calculating the value for K, at which point we can say whether or not the student lucked into the right answer or had the wrong answer. So Kc is NH3 squared over N2 times H2 cubed, because you got the 2 and the 3 coefficients become exponents, and you multiply the concentrations on each side. Throw in the values, pop them in our calculator, and we get Kc as 0.119. Now, of course, we should always look at the units. So perspective of that, ignoring the values, we've got concentration squared on top, concentration times concentration cubed on the bottom. So therefore, the concentration squared on top cancels out with 2 of the 3 of the concentration on the bottom there. And so we get 1 over concentration times concentration, or concentration to the -2, 1 over concentration squared, which is moles to the -2, decimeter to the 6th. Okay, so the value Kc 0.119 moles -2 decimeters to the 6th. Was the student correct? Yes, the student lucked in as K is less than 1. The equilibrium lies on the left, and so lucked into it, even though you cannot just look at the values unless they're crazy big or small, but you cannot look at the values and say immediately what K is. You do need to calculate it. Reversible reaction we've already seen once before, firstly studied in detail in gas and liquid phases and in solution. One study of the liquid mixture contained 0.714% NO2 by mass, calculate how many moles, blah, blah, blah. Now I'm doing this one just because it leads into a later question. Okay, so anyway, we're told 0.714% NO2 by mass in 25 grams. So that's the mass of NO2, 25, the total times 100, 0.714. So plug all that in and that gives us the mass of NO2, 0.179 grams. We wanted moles, so we divide it by the molar mass to get 0.00388 moles of NO2. Part B, both N2O4 and NO2 are soluble in a range of solvents, and equilibrium constant Kc can be measured in these. So first of all, let's get the equilibrium constant for this equilibrium. So it's going to be the righties, NO2, over the lefties, N2O4, bring in the coefficients that become exponents, so it's squared, and again, emphasize that these are the concentrations at equilibrium. We want the unit. Well, we've got concentration squared on top, concentration on the bottom. You'll get that cancelling out so that the actual unit is just concentration, or moles per cubic decimeter. Samples of 0.4 moles of N2O4 dissolved separately in 1 cubic decimeter of each of these solvents. So we've got particular solvent, right? Room temperature and reactions allowed to reach equilibrium. In one solution, the concentration of N2O4 at equilibrium, notice that at equilibrium, 5.81 times 10 to the minus 2 moles per cubic decimeter. Find the value of Kc in the solution and hence identify the solvent. We'll see where that comes from in a minute. So, emphasizing, this is what you have N2O4 at the start. This is what you have at equilibrium. Let's set up what I call a SCA chart. Other people call it an ice chart. Really, tomato, tomato, whatever. So we got at the start, the N2O4 was 0.4 moles per cubic decimeter, and we have none of the NO2. Change line, put in an X all over the place, bring in the coefficients. So the 2NO2 means that the NO2 change is twice the N2O4 change, and then make the reactants negative. Put all that together, you get 0.4 minus X and 2X. Now, when you get a SCA chart or an ice chart, the point is that it takes the equilibrium values down to expressed in one unknown X. And then at that stage, you say, well, either I know X, in which case I can calculate Kc, or I know Kc, in which case I can calculate X. What we want here is we're asked for Kc, so somehow we know X. And indeed, we look a little bit further in the question and we say that at equilibrium, the N2O4 is 5.81 times 10 to the minus 2. In other words, 0.4 minus X, which is the equilibrium N2O4, is 5.81 times 10 to the minus 2. Mess around with that. That gives us X is 0.3419. Replace everywhere we see an X in the equilibrium line by 0.3419, and so this was 2x, so it becomes 0.6838. Plug those into the equilibrium constant expression, and we find that Kc is 8.05 moles per cubic decimeter. Now it's the value of the equilibrium constant. The question also presented a list of solvents and what the equilibrium value was, or the equilibrium constant value in each of those solvents. So which solvent corresponds to our equilibrium constant value? Carbon tetrachloride, CCl4. Flask containing 0.1 moles ethanoic acid, 0.03 moles of methanol. So there's the ethanoic acid, there's the methanol, there's the equilibrium. Write an expression for Kc. Well, it's just going to be righties multiplied together over lefties multiplied together. Any coefficients become exponents. Well, it's 1 and 1 and 1 and 1 here, so no issues with the exponents. Units, well, you've got concentration times concentration over concentration times concentration. They all cancel out, so no units for this equilibrium constant. Calculate number of moles of ethanoic acid present at equilibrium. Well, we are told that the ethanoic acid required this volume of this concentration sodium hydroxide. When you're doing a neutralization like that, it's 1 sodium hydroxide to 1 acid. So therefore, we can just figure out the moles of sodium hydroxide is equal to 0.0400 moles of NaOH, and that's going to be equal to the moles of ethanoic acid. Again, this question, not really one in the equilibrium problem. It's much more of an acid-based problem, but no reason why we can't just calculate it here and knock it off quite nicely. So we got 0.04 moles of ethanoic acid. So calculate the value of the equilibrium constant, Kc, for this reaction. We know we start with 0.1 moles of ethanoic acid, 0.083 moles of methanol, and we also know, because we just calculated it, that at equilibrium we had 0.04 moles of ethanoic acid. So set up a SCA chart. At the start we have 0.1 of the CH3COH, 0.083 of the methanol, and none of the products. The change line, we'll put in X all over the place, bring in the coefficients, which is 1 and 1 and 1 and 1, make the reactants negative. Put it together at equilibrium, 0.1 minus x, 0.083 minus x, x and x. Again, the point of a SCA chart is you get all of the equilibrium values in terms of one variable x. So you either know Kc, in which case you can get x, or you are asked for Kc, in which case somehow you must know x. Well, we're asked for Kc here, thus we must know x. So let's use the calculation that we just did that tells us that at equilibrium we have 0.04 moles of ethanoic acid. In other words, 0.1 minus x is equal to 0.04, thus x is 0.06. So every time you see x put in 0.06, so the methanol becomes 0.1 minus 0.06, which is 0.04. The methanol becomes 0.083 moles minus x minus 0.06, that's 0.023, and then x and x just become 0.06 and 0.06. Pop those values in the Kc expression, pop them in our calculator, and Kc 3.91, and if you remember it is unitless because we got two concentrations on top and two concentrations on the bottom. Phosphorus forms two chlorides, PCl3, PCl5, dynamic equilibrium, blah, blah, blah. Write an expression for Kp. Well, it's exactly the same as Kc, except instead of using concentration, we use pressure. So righties multiplied together over lefties. Any coefficients become exponents, but they're all one here. So sealed vessel filled with PCl5. So we got that at the pressure of this. Upon heating, the system comes to equilibrium to form a mixture that contains PCl3 and of course also Cl2 at this partial pressure of 1.3 times 10 to the 5 pascals. So what's the partial pressure of Cl2 at equilibrium? Well, we only had PCl5 at the start. So every bit of reaction makes a PCl3 and a Cl2. So in other words, the pressure of Cl2 is the same as the pressure of PCl3. You think nice and easy, but a very important idea, a very important concept, the application of every time one of these reacts, you make one of those and one of those. So continuing on, calculate the value of the equilibrium constant Kp given its units. Well, Kp is the pressure of Cl3 at equilibrium that we're told, times the pressure of Cl2 at equilibrium that we're told, divided by the pressure of PCl5 at equilibrium. Okay, well, we know the PCl3 and the Cl2, but we don't know the PCl5 at equilibrium. We just know the PCl5 at the start. So pop in all those values, only PCl5 at the start, no PCl3, no Cl2. Put in the X lines. Everything's 1, so that makes it nice and easy. Minus X for the reactant, plus X's for the products. Put them together, and that's what you got. Again, when we have a SCA chart, the idea is that at equilibrium, we get all the values in terms of one variable, X. So we either know X, so we can get K, or we're asked for K, in which case we somehow must be told X. And we're told X here because, of course, the PCl3 at partial pressure 1.3 times 10 to the 5 is X. So everywhere we see X, replace it by 1.3 times 10 to the 5. So this becomes 1.7 times 10 to the 5, 3 minus 1.3. This becomes 1.3 times 10 to the 5, and this becomes 1.3 times 10 to the 5. Pop them in, calculate 9.9 times 10 to the 4. We do need to think about units. Well, we've got Pascal times Pascal on top, Pascal on the bottom, 1 Pascal each cancels, leaving us with pascals as the unit. Here's that nice pinky bluey one, but here we want to actually do some calculations. So what's the expression for Kc? Well, of course, it's righties over lefties multiplied using the coefficients, which here are a bit challenging because you've got 6 H2Os and 4 Cl minuses. Units of this, well, you're going to have concentration times concentration to the 6 on top, divided by concentration times concentration to the 4 on the bottom. Cancel out as appropriate, or multiply and then cancel out, and we get concentration squared, or moles to the cubic decimeter squared, which is of course mole squared, mole squared, decimeters to the minus 6, like that one. Same question, student carries out experiments starting with separate solutions of this and this. When they're mixed together, the concentrations of both this and this are 0.72 moles per cubic decimeter. When the mixture reaches equilibrium, the concentration of the water, right there, 0.744 moles per cubic decimeters. Calculate Kc. So again, set up our SCA chart. There are the starting values, 0.72 each of those, none of the COCl4, none of the H2O. Change will be XXX, bring in the coefficients, that's 1, 4, 1, and 6, and then make the reactants negative. So at equilibrium, 0.72 minus X, 0.72 minus 4X, X, and 6X. Now, again, we're asked for Kc, which means somehow we must know X. How are we told X? Well, when the mixture reaches equilibrium, the concentration of the water is 0.744. Thus, 6X is 0.744. X is 0.124. So every time we see X, we'll put in 0.124. So this becomes 0.596. This one becomes 0.224. This is, of course, 0.124. And this is 0.744. Pop those into the Kc expression, calculate it, and we get 14 moles squared, decimeter to the minus 6 units, of course, what we calculated or determined on the previous slide. Back to our favorite industrial process, N2 plus 3H2 goes to 2NH3. Write out the Kp for this expression. Well, it's pressure, so righties over lefties, so it's the pressure of NH3 over the pressure of N2 times the pressure of H2. Don't forget to turn the coefficients into exponents, so it's the NH3 squared and the H2 cubed. That was it for that part. So part 2, calculate the equilibrium partial pressures of hydrogen and ammonia. Use these to calculate the value for Kp. Well, let's see what we've got. Put in some pretty colors. The initial nitrogen was 26, the initial hydrogen was 82, and the equilibrium nitrogen was 18. So let's set up a SCA chart. At the start, we have 26 for the nitrogen, 82 for the hydrogen, none for the ammonia. Change line, well, it's X for everything. Bring down the coefficients, so that's 3 there and 2 there, and make the reactants negative. Put all those together for an equilibrium, 26 minus X, 82 minus 3X, and 2X. Again, the idea of the SCA chart is all the equilibrium values are in terms of now one variable X. So if we know X, we can get K. If we know K, we can get X. Well, in this case, we're asked to calculate K, so somehow we're told X. What bit of information have we not used? That the equilibrium partial pressure of nitrogen was 18. So in other words, 26 minus X is 18, X is 8. So putting that in everywhere, 26 minus 8 is 18, we knew that. 82 minus 3/8 is 58, and 2 times 8 is 16. Pop that into the Kp expression, and we get 7.3 times 10 to the minus 5. Get in the units, we got atmosphere squared on top. We've got atmosphere cubed on the bottom, so we'll calculate, cross out the whole atmospheres on top with 2 of the 3 on the bottom. And we get 1 over atmosphere squared, or atmosphere to the minus 2. A nice fun question to wrap up with. Chromium 6 present as the anions dichromate, and chromium 6. They can be interconverted in solution with this equilibrium being established. So the first thing, write an expression for Kc. Well, it's the righties. So CrO4, 2 minus, H plus multiplied, got coefficients of 2 for both of those, so it's squared. And then on the bottom, the dichromate times the water, just one of each of those, so nothing special. Units, we've got concentration squared, so concentration to the fourth on top, concentration times concentration, concentration squared on bottom. 4 over 2 leaves us with 2. Mass of water in 1 cubic centimeter is 1 gram. Show the concentration of water in any dilute aqueous solution, 55.5 moles per cubic decimeter. Again, this is not a question that really belongs here, but we might as well do it because we'll need it for the next part. So 1 cubic decimeter of solution is going to therefore weigh 1,000 grams. Okay, and 1,000 grams is 55.5 moles of H2O. So the concentration of water in moles per cubic decimeter is 55 moles in 1 cubic decimeter, or 55.5 moles per cubic decimeter. Always the concentration of water in dilute aqueous solutions. You rarely have to use it, but it's always 55.5555555, etc. So, solution prepared containing equal concentrations of the dichromate and the chromate. The concentration of each was 0.057. A student predicted that a solution containing equal amounts and both should be neutral. Is the student correct? Well, we know Kc is that. We know the value of Kc, 2.42 times 10 to the minus 15. We know the concentration of chromate, it is 0.057. We know the concentration of dichromate, it is 0.057. And we know the concentration of water, because we've just figured it out, 55.5. So the only thing here we don't know in such a solution with equal concentrations is the H+. So punch all that in your calculator. You get H plus squared is 2.36 times 10 to the minus 12. H plus 1.533 times 10 to the minus 6. The pH is minus the log of the H plus is 5.81. So therefore the student is incorrect because it's not neutral. It is a teeny bit acidic. So there we are, the equilibrium A-level calculations. Hopefully nice and fun.